You don't have to write these down there in front of you. We did linear, we did cubic, and then we did quintic. What did we know about all three of those graphs? We know that they disco. We know that the linears disco straight, the cubics do like a little disco, and then they can do like a really wonky one. And then the quintics just do an extra bump in there as well, right? That's what we do know. We do know that their domains are x such that x is an element of the reals, or negative infinity to positive infinity, and the range is the same because they disco. Their arms are going out to infinity both directions. So linear could be like this. Cubic can be like this little swoopy thing, called point of inflection, or it can have a max and a min. And your quintics could actually do the swoopy thing like that, point of inflection, or a couple mins and a couple maxes. Now the ones I drew all are going up on the right. So what do we know about these graphs for every single one of them? Yeah, all these graphs above have positive leading coefficients. Wow, I was really consistent on my y-intercepts as well. So, unintentional, but this one has a y-intercept that is positive. This one has a y-intercept that's positive. This one has a y-intercept that's positive. This one has a y-intercept that's positive. So what can you tell me about all of the constants of every single one of those graphs? Yeah. So the constants of all the graphs, the red graphs, the constants are positive. So getting an equation without variables and just having to graph it, probably not going to happen, because you could just type it into your calculator and poof, get an equation, or get a graph, right? So often what they'll do is they'll say something like this. Y equals ax cubed plus bx squared plus cx plus d, where a is greater than 0 and d is less than 0. And then they want you to sketch a graph. So if a is greater than 0, bless you, a is my leading coefficient, and my leading coefficient then is what? Positive. So then my graph is what? Up on the right. So if a is greater than 0, I know it's up on the right, and because it's a degree 3, I know it's down on the left, because it discos. It's opposite, correct? Okay. If d is less than 0, d at the back is my what? My constant, and my constant is my what? And why is it my y-intercept? Because if I fill 0 in for x's, these all go away, and I'm left with just my constant. Therefore, my y-intercept, because y-intercept is when x equals 0, right? So I know that I have a negative y-intercept. So if that's all the info they gave you, you just draw yourself like a triple squiggle. You know, cool, like that. Where it's up on the right, down on the left, and you need a negative y-intercept. So if I go like this, I need it to be up on the right, down on the left. So I can start down here, and it's just like, and then I'm like, you need to take a hard turn here because we need it to be a negative y-intercept. Okay? These are symmetrical as well. So some people will do this. Oof. I see the craziest things. And I'm like, there is no cubic that looks like that. Okay? That's bad. Don't do that. They're like, but it went through the negative and it's up on the right. I'm like, but it's not a cubic function. I don't even know what that is. It looks like a death trap. Just stand on here and chunk. And then you just like work your way back out of the hill. You know? This is a canyon. It looks like someone's... So this is just a quick summary of cubic, linear, and quintic, because we did odd degrees. They're all odd degrees. They disco, correct? Then we're going to do only 2 even degrees. We're going to look at 2 even degree functions because we have to stop at degree 5, right? So we have quadratics, which we did last year, and then quartics, which is new this year. So we're going to do degree 2. Oh, degree 2. Sneezy. And it's called a quadratic. And we know that because we did these last year. So, I'm going to get you to type into your calculator y equals x squared plus 3x plus 2. And then I'm going to get you to type in y equals negative x squared minus 4x plus 5. And sketch them quickly. Just like, I don't want you to go find the x and y intercepts or anything. I just want a literal sketch off the calculator. So, we can do this actually quite quickly in our heads if we really want to, because I gave you this one. I can go x plus 2 and x plus 1 as my factors. So my x-intercepts are at negative 2 and negative 1. My y-intercept is at 2. And I know my leading coefficient is positive, so I know it's upwards. Can I get my minimum really quickly off of this? Off this equation? No, I'd actually have to complete the square. Complete the square is when you went like plus blank minus blank and you forced it into being the quadratic into being in vertex form. Yeah, we don't have to do that this year. So, if they ask you to find mins, wow, I just did what I told you not to do. There we go, it's perfect. So, if they ask you for mins and maxes off of these ones, you can use your technology for that. And I'll show you that in the curriculum, it shows you that too. Okay, this one here is concave down. I have to decomp. Negative x squared minus 5x plus 1x. Why I went with the 5 and the 1 like that, I'm not sure. So our x-intercept is at positive 1 and negative 5. And it's going to be something like, a little something like this. I don't know. This has to be 5. And it has to be down on right. Whoa, what's happening? What is happening? No discoing. Isn't you just like, I'm tough? Or I'm scared. I'm scared. Oh, good find. I'm scared. Hands up. I'm in trouble. And then I'm tough. If you're negative, you're tough. If you're positive, you're scared. I don't know. But your arms are in the same direction, correct? But what didn't change is if I have a positive leading coefficient, my right is still up, right? The way it ends on the right did not change based off my leading coefficient. But the degree is what tells you how it ends on the left, right? And all of the other ones ended in the opposite direction because they discoed. Odd degrees. So degree 1, degree 3, degree 5, they disco. So I know my arms are in the opposite directions. This one, I know I have a positive leading coefficient, so I know it's up on the right. That didn't change, even though this is degree 2, correct? That didn't change. However, because it's degree 2, I also know it's up on the left as well. Okay? This one has a negative leading coefficient, so it's down on the right. And because it's degree 2, I know it's, I wanted to draw the other way, down on the left. And my constant is still the y-intercept, we agree? That didn't change. What about my domain? If I'm tough, is it still going out for life? If I'm scared, is it still going out for life? Yes. So what's the domain of these ones? X and element of the reals. So for every polynomial, actually, your domain is x and element of the reals, unless it's a word problem. Because word problems could involve time as your x. Well, you can't have negative time, right? It could involve like a standard measure of like inches. Well, you can't have negative inches. You could have nothing, or you can measure longer than that. That's about it. Okay? So your domain is going to be x such that x and element of the reals if it's just a plain old equation. Or in interval notation, negative infinity, positive infinity. The range, though, the range is different. Just so you know, everything you guys say over there gets picked up on this thing. It's wicked.
We are now.
So, this one is concave up, right? This one is concave up. We talked about that last year. It opens up. So it has a minimum. The lowest point, correct? Is there anything below that? No, the whole graph is above it. So when we had a minimum last year, our range would be y such that y is greater than or equal to whatever the minimum was. Because the whole graph is greater than that. In interval notation, if it's greater than a specific value, Let's pretend it's a number line because it's interval, right? It's on a number line. So it's going to be at this value and then greater, right? Well, what does that represent? This would be my minimum, this dot, and then this would be positive infinity, right? That right arrow. So in interval notation, it's going to be to positive infinity and a minimum, because you always go left to right. Infinity has to be a round bracket. What does this one have to be? Square, because it's equal to. Now when it's concave down, your domain is still XCR, but your range now, you have a maximum. So your entire graph is less than it. So we're going to have y such that y is less than, and it's still equal to it because there's a value there, right? Less than or equal to your maximum. YER. And in a number line, if here's your maximum, I have a closed dot that's equal to, we would be this way to this arrow, right? And what's this arrow? Negative infinity. You list them in order. See? You see that? So it would be like this. Negative infinity to maximum. Calculus only uses interval notation. They don't use set. They don't use the squiggly brackets. Math 30-1, interchangeable. They can ask for either. And if on a written response they ask for interval and you give them set, nothing. Which would suck. Okay, how many x-intercepts does this have? 2 or 1 or 0. Remember, the maximum number of x-intercepts is equal to the degree. And these ones can actually have 0 because they're both up or both down, right? The whole graph could be completely above the x-axis. When it disk goes, at some point it's going to have to go through, right? But these ones don't have to. So I could have 0 x-intercepts, or I could have 1 where it just runs tangent. Or I could have 2. So the difference between degree 1, degree 3, and degree 5 is they minimum out at how many x-intercepts? Degree 1, 3, and 5. Because if it's disk going, it's going to have to go through at some point, right? They maximum still at the same degree, but they minimum out at 1, so they could have 1, 2, 3, 1, 2, 3, 4, 5. Depends on what they are, right? The difference between degree 2 and degree 4 is they minimum out at 0, and they still maximum out at degree. So that's the difference between the even and odd degrees. Comes up in multiple choice on diplomas all the time, asking questions like that. Okay. So that's degree 2. We've done those. Then we have quadratic, which is degree 4. I used to love teaching these. My last name used to be Wagner, and I'd always be like, Wagner, positive. So when it made a W, and you could write Wagner, then it was a positive graph. And then if it wrote math, which is totally illegal in AP, but whatever, and in my mind, it would be negative. And some people are like, oh yeah, I kind of remember that. It's the opposite of what you think, because you think math's a positive thing, you know? So just think opposite of you. So, and if you don't think math's positive, I don't know why you're here, because this is like an all-long first period. You just don't escape it. Yeah. Okay? So, say we have y equals x4 plus 3x cubed minus 2x minus 5. I skipped the squared, I don't care. Put that into your calculator and give it a quick sketch. So, it's degree 4 and it's positive leading coefficient, so it's up on the right. And if it's up on the right and it's an even degree, it would be up on the left, correct? If I gave you a positive leading coefficient and it was degree 50, it would be up on the right and up on the left because it's an even degree. It wouldn't matter what degree I give you. If it's an even degree, they end in the same direction. If it's an odd degree, they end in opposites. So it's up on the right, which means it's also up on the left. It bothers me that I put right on the left and left on right, but I don't switch it. So that's good. It doesn't bother me that bad, I guess. And then this would be my constant, which is my y-intercept. So I know the y-intercept of this graph is 0 and negative 5. What's the domain of these ones? X, and I'm in the real. Still going everywhere, right? So sad the person watching this doesn't get to see my thing. Yeah. Radical graphs are sideways. Log graphs are kind of sideways. Yeah. Inverses of these make them sideways as well. All right. What's the range? It's the same thing as a quadratic, except I have a minimum. I don't remember which one's lower. This one. It's not drawn accurately. So this is a minimum, correct? So the graph is all what? All higher than that, isn't it? Do you remember how to find minimums? Oh, I still need to get a calculator on this thing. So we're going to go. We want to calculate something. Calculator. So we want to do these, and we want to find the minimum for this. Now there's two minimums. Which one do I care about for range? The lowest one. So we're going to go second trace. And why do we pick second trace? Because we want to calculate something. And that's where we go when we want to calculate something, because the word behind trace is calculate, and you're pressing second that. So calculate. Minimum 3. So I need to be on the left bound of it somewhere over here. Then enter. Then on the right bound of it somewhere over here. Then enter. So left bound, enter. Right bound, enter, enter. So my range for this one is actually y such that y is greater than or equal to negative 9.15, I'm going to say. Y. And then greater than negative, so if I drew this would be negative 9.15, and it's greater than it. So it's this way, number line here, it's a closed dot. What does this represent? Infinity. So often it's easier for people to do interval notation if they draw the number line, because you just literally put a comma in that bad boy. This one's round, this one's square, because it's equal to. So whenever I teach interval notation, I do number lines, because it makes people not put the numbers on the wrong spot. Okay? How many x-intercepts can this have? 4. It could have 2. It could have 0. This one has 2. Yeah. So the minimum this one can have is, the maximum it can have is, and then it can have any variation in between. 0, 1, 2, 3, or 4. Okay? So this one has 2. But the number of x-intercepts of a quartic, 0, 1, 2, 3, 4. And now we're going to go to the notes that I handed out to you. So they look like this. So if you look here, they talk about zeros of multiplicity 1, multiplicity 2, multiplicity 3. So 0 of multiplicity 1, these all have zeros of multiplicity 1, or x-intercepts of multiplicity 1, or roots of multiplicity 1, because they go straight through. So when you have an x-intercept and you have 1 at it, it hits that 1 and it just shoots through. Okay, that's a multiplicity 1, there's 1 root. Now this one here would actually be a multiplicity 1, correct? So because it hits it and shoots straight through. So whenever there's a straight line, no deflection, it shoots straight through. This one hits it and it wants to go straight through, but then it hits it again and it bounces it back up. Now this is a root of multiplicity 2, minimally. A root of multiplicity 2, minimally. So the smallest root, the smallest multiplicity of root this one can have is 2. But it could also have 4, or 6, or 8, or 10, or 12, or whatever. Because all that happens is this down here will get wider. So like if you had, say, 10 there, it will come down, and then it'll hit it, bounce, 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 and then shoot back up. So it's just a longer drag is what it'll look like on your calculator. But often on a diploma, they'll ask for the minimal possible multiplicity, so that you all have to find the same equation, right? Then it's forcing you to all use it as 2. Okay? This is called the point of tangency. I told you that before. Now this one where it has a multiplicity of 3, what happens is it hits it again, and it tries to bounce it down like tangent, but there's 3 there, so it actually sends it up. So like there's 1, would go straight through, 2 would bounce it down, oh, but there's a 3rd, so it bounces it up. So that's where you get this little S curve through it. So multiplicity 3 minimally, or 5, 7, 9, 11, etc. It's called the point of inflection. It inflects there. This little blue dropping down here is nothing. I'm just proving a point. All right. So for each of the following polynomial functions, we're going to determine the least possible degree. So what's the least possible degree of this baby? We know it needs to be an odd degree because it's discoing, right? It can't be linear because a linear would be a straight line. Could it be a degree 3? Yes, a degree 3 can have at maximum 1 minimum and 1 maximum, and this one has 1 minimum and 1 maximum, right? So the least possible degree this one could have is 3. What's the sign of the leading coefficient? Why do you know that? It's up on the left and it's down on the right, so it's a negative leading coefficient. Can I write LC? All right. The x-intercepts, what's the least? Well, this x-intercepts, how much does this one have? This one has 2. That particular graph, because it's a degree 3, what's the least it could have? It could have 1. This one actually has, and I want you to point this out, this one is at x equals -4, and I can just say that. I'm done. Right? Because it only had 1 through it, because it was straight. It's a multiplicity 1. You don't have to write multiplicity 1. It's the only one you don't have to write. This one here, and the reason why it says least possible degree is for my multiplicities. So this has to be the least possible degree it could be. The least possible degree would mean how many are here? 2, right? If I didn't say least possible degree, there could be 4 or 6 or 8. So that's why I have to say least so that everyone writes the same answer. Okay? So this would be at x equals 1 multiplicity 2. And what would the equation be? Ready? Ready? Okay, I feel like a cheerleader again. Okay, how do we get an equation? Well, in the past, the equations we've used, correct, were always ones without brackets. Yes? Because then it gave us the constant at the back, which is our y-intercept, and it gave us a leading coefficient. Now, when you're coming up with equations of graphs, you guys are going to try to do it in that format. Well, how do I come up with the equation of a graph in that format when all I can say is, hey, it has to have a negative leading coefficient and the last number needs to be -4? I don't know what the middle is, right? So everyone tries to put in that format. You can't. Every time you're coming up with a graph of a polynomial, and you guys did this last year, you did it for a quadratic, always. What you did was, you guys could put it into vertex form, but we don't have a vertex form for a degree 3 or a degree 5 or whatever. So what we're always going to do to come up with an equation is we're always going to go y equals, and I used to always go a here. But then I found that they used a on the diploma and it confused you completely. The leading coefficient can be anything. It can be a, m, smiley face, p, r, snake. It could be whatever you want it to be. I would make it not be snake. But I'm going to make it be m because I've never seen them use an m before. And I'll show you. Yeah. When I put a, the problem with a is they'll go, determine the leading coefficient 1 over a, and then you guys get what a is. But it's 1 over a. They're just asking for their a, not the leading coefficient a. They just want what's down here, right? So it confuses people. So I'm choosing m. Okay? Then what you do is you always follow behind with your factors. These are your factors. That's how we're going to come up with equations of polynomials always. Your factors come from your what? Your x-intercepts, right? Because your x-intercepts are just the solving of your factors. That's what we figured out in the earlier parts. So I always teach this lesson last instead of earlier. Okay, so what are my x-intercepts here? X equals -4. I'm going to write it up here to help myself out. And then x equals 1 multiplicity 2. This is where the error lies, is in the multiplicity 2. Multiplicity 2. You guys don't include the 2. Multiplicity 2 means there's how many there? 2. As a factor, how would I represent that? Squared, or I'd write it out twice. Those are my two options, right? You often will forget the squared, and then you'll get the wrong a, and it stinks. It sucks. Because then I'm like, squared, you're like, oh, when you get your test back, most angry, because you're like, I knew that. Okay? It's worse when you do a question, you're completely lost. You're like, well, I was completely lost. But when you make a stupid error, you're like, oh, I knew that. That bothers me more than when I'm just completely lost. I'm like, well, I didn't know how to do it. It's fine. Okay? So, my factor for this is going to be, for x equals -4 is x plus 4, because I'd work my way back by adding a 4, right? This one, x equals 1, is going to be x minus 1, because I'd move it back, but I'm going to have a squared. So when people remember the squared, they're happy. The catch, though, is what's most forgotten, and I'm going to highlight it because it's forgotten way too much, is this. Our leading coefficient. Okay, let's try this out. You do this for me. Type into your calculators so I can prove a point. Don't write this anywhere. You're just going to type it into your calculators. I'm going to erase it after. Y equals x squared plus 3x. No, I'm going to do it in the format you have. X plus 3, x plus 2. Type that into your y1. Into your y2, type in 2, x plus 3, x plus 2. What doesn't change? The x-intercepts do not change, right? Because they're both still going to be negative 3 and negative 2. We agree? What about the y-intercept? It changed. Why would it change? Because when I find the y-intercept, I actually put zeros in for these, right? So this one would be 6. I put a 0 in for this one. 2 times 3 times 2 is actually 12. It totally changes my y-intercept, doesn't it? So if you don't find out this leading coefficient, your x-intercepts will be just fine, but your y-intercept might be complete garbage. Does that make sense? So that's why it's so important to find this, and people forget to do it all the time. So let's go through and see if we can actually come up with the equation now. So we have y equals m, I'm going to find, because I don't know what it is. And then I have x plus 4 and x minus 1 squared. Did you do what? Nope, not yet, because we're going to solve it and hope to get a negative, right? Because that's what we're looking for. So what was the thing that changed that leading coefficient? What was the thing on your graph that changed? Your y-intercept changed. And actually every other coordinate changed. The only thing that didn't change was my x-intercept. So I can't use an x-intercept to solve for m. I can use any other point on the graph, but I can't use an x-intercept. Often on the diploma, there's a point that's bolded. If there's a bolded point, be like, it must be important. They must want me to use that. I think it's true. Okay? So if this was my test, I would have bolded this one. Now people will tell me it's negative 2. Please watch your scale. Each of these ticks is actually 2, so that's negative 4. So my coordinate I'm going to use is 0 and negative 4. And that's an x and a y. Do I have to use the y-intercept? No. Any coordinate on there but an x-intercept I can use, because everything else moves, right? However, that one was an obvious one. I'm not going to pick it looks like approximately 1.3 and 2.8. Don't do that. That's bad. Go through one that goes through a little intersection. If it's bolded, use it. So why would I need a coordinate? Yes.
So you can plug in for the x and the y.
And solve for the?
M.
Yes. Genius. Okay. Negative 4 equals m. 0 plus 4, 0 minus 1 squared. So I get negative 4 equals m. And then I get a 4. And then I get a positive 1. Do you see how if I forget the squared, it's going to mess this completely up? Right? So when it has multiplicities, or when it has tangents, or when it has inflections, you have to spot those. Okay, so I get negative 4 equals 4m, divide by 4, and m equals, ooh, that's sticky down here. I don't know what's going on, but it won't let me write. Negative, whoa, negative 1. And then people will box this and they're like, there you go, Lepp, you're welcome. And I'm like, I don't have an equation. I have this m, of which I'm not even sure what it is. Yeah. Yeah. So you actually have to do one more step. This in there, right? So it's y equals negative 1. You don't have to write the 1. You have to write the negative sign, though. Make sense? Yeah.
I'm still confused on how we're figuring out like the degree of it. Like, the least possible degree.
Okay, because it's discoing,
Yeah.
we know that's a 1, 3, or 5. Because it's not a straight line, the next minimum it could possibly be is a 3. The only reason why I know it can be a 3 is a degree 3 can do that S shape, so it can have a min and a max. And this one has 1 min and 1 max. If this had 2 mins and 2 maxes, it would be 5. Does that make sense? All right. We're going to go through B. So, least possible degree of B. 4. Can't be a 2 because, yeah, it would just be like a smiley face. It would be like a parabola, right? And this one's got a little too many curves going on. I could also write the name Wagner and really messy W, right? So, 4. Where am I going with that? What is the sign of the leading coefficient? Positive, because I always look at the right arm, and the right arm is up. So I have an up on the right, so it's positive. Now my x-intercepts, I'm going to write them up here, but then I'll transfer them down there. This one's at -4. Do I have to write multiplicity 1? No, only thing I don't have to write. Straight through. This one is curving right here. What makes this S thing? Look through. So this one is at x equals 3. What do I have to say? Multiplicity. And what is this called? The point of what? Do you remember? Inflection. So that's here. X equals -4, x equals 3 multiplicity. Okay, then we need to come up with the equation. So we're going to go y equals m, x plus 4. And then this one is x minus 3 cubed. If you give me this with the x-intercept, you're actually wrong. So that's why I'm going with this, because those are the x-intercepts. These are the factors, right? Now, how do I finish this off? I actually have to go look for a what? Yeah, point on the graph, right?
Yeah. The least cost or the x-intercepts least possible to be reducing 3.
Yes, that's why I just said multiplicity 3. Because it could have a 5, it could have 7 there, it could have 9 there, right? But we all have to pick to the slowest, to the lowest one, to the slowest one. Oh my goodness. Okay, so the one that I see it going through, crappiest, I'm going to say here. Like I said, on my tests and on the diploma, they'll bold something so that you're not guessing if it's going right through it. So this one here would be at 5 and 8. The only point I can't use are the x-intercepts, right? Because they're the only ones that don't change. So it was 5 and 8. We'll give my x and my y. So I'm going to go 8 equals m, 5 plus 4, 5 minus 3 cubed. 8 equals m times 9. And this is 2 cubed, which is 8. 8 equals 72m. So m equals 1/9. And then I have to write the equation with the m in it. So y equals 1/9 x plus 4, x minus 3 cubed. Now, we can always go back and check a little here. So I can go 1/9, right? Take the 1/9, and it should be positive because I need a positive leading coefficient, right? I can also check my y-intercepts. Y-intercept, what should you immediately think when you say y-intercept? X equals 0. So I should be able to put a 0 in here, a 0 in here, multiply it all out, and get the y-intercept on my graph, right? So let's check it. Okay, you have just a tiny bit of homework. Because I'm just making you do only the equations of the graph, because we're going to do other stuff.
Because it's like this one. And the least you have there is 3, but it could be 5, 7. Huh? Like, look, they're like it's like S, but it's like it's not bouncing straight off. It's like, yeah, it's like chilling. It's more like an S.